In this video, we're going to look at a Daniell cell. And a Daniell cell is just a really simple type of galvanic cell. And again, remember, a galvanic cell was the type where we have a spontaneous chemical reaction driving or producing an electric current. And we said that those reactions that we're going to see in this chapter are oxidation reduction reactions. So the one that we're going to use here is just a really simple one. I'm going to have zinc solid, reacting with copper ions. And there would be some sort of cation with it or anion with it. Let's just write it. Probably something like copper 2 sulfate. I would then produce copper solid and zinc sulfate. And then we know that copper sulfate is actually soluble using our solubility rules. So it would dissociate into ions, same with my zinc sulfate, and then sulfate would be a spectator ion and it just gets canceled out. So that's why I generally don't include it. But again, do note, you're not going to go into a lab setting and just get a bottle of a cation, right? There's going to be some corresponding anion with it. It's just that in this case, it's a spectator ion, so we're just going to ignore it. If we were to assign oxidation numbers to all of these, oxygen is going to be a -2 on both sides, and sulfur is going to be a +6 on both sides. So the oxidation number of those are not changing. What I do have, though, is I have an oxidation number of 0 on zinc here, and then +2 over here. So zinc is being oxidized, right? It's losing electrons. Here, copper is +2, right? Again, these are monoatomic ions, so my oxidation number is numerically the same as the charge. Here, it's 0, right? It's its elemental form, so I'm going from +2 to 0. It is gaining electrons, so it is reduced. So my two half reactions, right? I have zinc solid going to zinc 2+, and then I have copper 2+ going to copper solid. And then using our methods for balancing these, right, we would balance all atoms other than oxygen and hydrogen. They are. Balance oxygen and hydrogen, I don't have any. Then I balance charge by adding electrons. So I need to add 2 electrons to the product side of our first half reaction, right? I had a +2 charge here. I had no charge over here. So by adding 2 electrons, I have a net charge on 0 on both the reactant and product side of that equation. And then for this one, I need to add the 2 electrons to that side, right? A +2 and a -2 gives me 0. I have no charge over here, so 0 on both sides. So these would be my 2 half reactions. If we were to continue balancing this, we would want to make the electron counts equal, which they are, and then we could just add them together. So up here, this is my oxidation half reaction. And this one is my reduction half reaction. Remember, in an oxidation, we're losing electrons. So electrons are something I'm producing or giving off. It's going to be on the product side, right? A reduction is gaining electrons. It's something we're adding to it. It's going to be on my reactant side. And then the way that our Daniell cell is going to work, or our galvanic cell, is what we're going to do is we're going to have 2 separate containers. We'll draw this out here in a minute. We're going to have the oxidation half reaction on one side. We're going to have the reduction half reaction on the other side, and we're going to connect those with an electrically conducting wire. So what's going to happen, these electrons that we're producing, we need to give to copper 2+. So they're going to move across that wire. The flow of electrons is our electric current. So essentially, we're just separating out these 2 reactions and connecting them with a wire. So these electrons that we're losing, right, can be added to copper 2+. So that's kind of the general plan. So again, the type we're going to look at is a Daniell cell. And again, it's just a type of galvanic cell. Sometimes they just call it a galvanic cell. So my directions on a test or a quiz, I could say draw a galvanic cell. We're only going to use Daniell cells, so you can just really think of those as the same. So it's going to consist of 2 half cells, right? One for our oxidation and one for the reduction. And then the 2 half cells are connected. And in fact, let's actually add a little bit more detail. The solid metal, right? I do have solid in both cases, right? I have a zinc solid and a copper solid, and we'll talk about later what happens if I don't have one. But the solid metals are going to be called electrodes. And then the electrodes are connected with a piece of electrically conducting wire. The electrons then will flow from the oxidation half reaction to the reduction half reaction across that wire. That flow of electrons is our electric current. So the electrons will move across the wire from the oxidation half reaction to the reduction half reaction. They're also connected by what's called a salt bridge. And when I say they, I'm sorry, I mean the half cells. And what our salt bridge is, often it's a tube. It could be really anything, but it contains an inert electrolyte. So it contains an ionic substance, and its purpose is to try to keep the neutrality, or to keep our solutions neutral, right? Electrons are leaving one side, so it's going to become positive. It's going to the other side, which is becoming negative, and we need to have some ions to kind of counteract that, to keep the solutions from becoming really negative or positive on one end. And I'll add more details here when we draw it out. But this is essentially what we're doing. We're going to separate the 2 half cells. We're going to connect the metal with a piece of wire. Electrons are going to flow across that wire to get from the oxidation side to the reduction side. That's our electric current. And then to maintain the electric neutrality of our solution, we're going to have a salt bridge. We could write that here. It contains an inert electrolyte. So let's draw this. So I'm going to have 2 essentially beakers, and these are going to be my half cells. And then in there, I'm going to have my piece of solid metal. And then I'm going to have that in a solution. I'm going to have my oxidation half reaction on this side and my reduction on the other side. You can have them switched. Just make sure if you're switched, when I show the direction of the electron flow, you have your electrons going the other way. I'm going to connect these electrodes with my wire. Oops, sorry about that, guys. So my oxidation half reaction, the piece of metal, right, we said these are called electrodes, it's actually called an anode. So the anode is going to be my oxidation side. And then the reduction side is going to be called my cathode. Our cathode has a positive, is usually given a positive symbol just to kind of represent it. So if you see a positive there, it's representing our cathode. And then our anode is given a negative. So kind of some ways to remember those. Remember, cations have a positive charge. So cation, positive charge. Anions have a negative charge, so anode, my negative charge. And then to know which one's the oxidation and which one's the reduction, the way I remember it is that oxidation and anode both begin in a vowel, where reduction and cathode both begin in consonants. So how, if you could just remember, it's fine, but I just remember usually the vowels. So the oxidation side is going to be my anode, the reduction side is going to be my cathode. And then we are going to use this example that I had up here. So I'm just going to copy it down so we have it on the same page. I'm going to move it around a little bit, so just kind of hold off. I just didn't want to have to keep scrolling up. So my anode side, right, that's my oxidation. That's going to be my zinc. So I'm just going to write it a little bit smaller right here. We're going to get rid of the other one. So going to zinc 2 plus my 2 electrons. So what that means is that this piece of solid metal is zinc. So this is zinc solid. And then floating around in solution, I have zinc ions. I probably also have those sulfate ions, right? They're spectator ions, but that doesn't mean they don't exist. They are floating around in solution. Over here, I'm adding my 2 electrons to copper 2 plus to produce copper solid. So labeling my electrode, this is copper solid. And then I do have copper 2 plus ions floating around, and then also some sulfate ions. And then we'll just get this out of our way. Our electrons then, right, we said they're going to flow from our oxidation half reaction, right? This is where we're producing them, right? They're produced at the anode side because that's where we're producing the electrons. That's where we're giving them the negative sign. So this side is producing the electrons, right? They're being given off, it's oxidized, we're losing them from zinc, resulting in electrons. Here, we're consuming the electrons. They're being attracted to the positive side. You can think about it that way if it helps. So my electrons then are moving across my wire in this direction. If you were to have your anode and cathode switched, right, if you had your cathode on the left and your anode on the right, the arrows for your electrons, right, make sure you have them facing in the opposite direction. And then if we had a light bulb here, this is going to be a really lame picture of a light bulb, but if this was a light bulb, we could light it up, right? We're producing electric current. We still have the salt bridge to put in there. So our salt bridge, in this case, it's going to be kind of a glass U-shaped tube. And then in that tube, we have that electrolyte. A common electrolyte is going to be sodium sulfate. And our cations are going to go towards our cathode, and our anions are going to go towards our anode. So in the tube, I have sodium ions, and they're going towards the cathode. And then I have sulfate ions, that's a little, and they're going towards the cathode. And it could be any inert electrolyte, it's just that's a really common one, so that's what we're going to include. So again, cations go towards the cathode, anions go to the anode. The reason for that, right, is we're adding electrons to this side. So we're getting a lot of electrons in here, right? It's becoming negative. So these positive ions are going to this side to help make it more neutral. Here I'm losing electrons, so it's becoming more positive. Our negative anion is going to go this way again to help maintain some neutrality for a while. And this is essentially our Daniell cell, right? We're just taking our oxidation half reaction, we're separating it from our reduction half reaction with a piece of wire that the electrons are going to flow across, creating our electric current. So let's look at another example. So we're going to design a galvanic cell. I could say Daniell cell. That uses the following reaction. And we're going to have lead 2 plus zinc solid going to lead solid plus zinc 2 plus. And we can use sodium sulfate again in the salt bridge. Sometimes I forget to tell you what to use. Sodium sulfate's always a good choice. Just pick something that's inert. So when I say design a galvanic cell, basically what I'm looking for is this picture. So we want to draw our 2 half cells, we want to label our electrodes, we want to connect them with the wire, show the flow of the electrons, add our salt bridge, show which way they're moving, label anode, cathode, that sort of thing. So replicate this using our new reaction. So the first thing I like to do is just determine which is my reduction and which is my oxidation half reaction. So I'm going to split these. I have lead 2 plus going to lead solid, and I need 2 electrons on this side, right? My oxidation number is going from +2 to 0, right? It's gaining electrons, it's being reduced. So this is my reduction half reaction. Right, this is going to be the side that's going to be my cathode. My other half reaction, zinc solid going to zinc 2 plus 2 electrons, right? My oxidation number is going from 0 to a +2. It's losing electrons. The electrons are something I'm producing. This is my oxidation half reaction, and it's going to be the one that occurs at my anode. So drawing these out, so my 2 beakers or 2 containers, my metal electrodes that got really kind of misshapen. I'm going to connect those, not erase those. And then it is standard, you don't have to do it this way, like I said earlier, but it is standard to draw our anode on the left. And again, you don't have to, just make sure that you have this electron flow going in the right direction. From our anode, right, it's the one producing electrons, to the cathode, it's the ones consuming them. I am going to put my anode over here though. So this is going to be my anode, which is our oxidation. It's going to be my negative electrode. I'm going to have my cathode over here. That's where my reduction is going to occur. It's going to be labeled as my positively charged electrode. And then zinc solid. I have some zinc ions in solution. This time I have lead solid, some lead ions in solution. I didn't tell you what its corresponding anion was, but they would be floating around also. My electrons are moving in this direction, right? They're going from my anode to my cathode, right? This is the zinc solid going to zinc 2 plus 2 electrons, and then those 2 electrons are adding to lead 2 plus to produce lead solid. So those are my half reactions. I do need to put my salt bridge in here still. And I have sodium sulfate, so sodium, I do have 2 for every 1 sulfate. They're going towards the cathode compartment, and then my anions are going towards the anode compartment. So this would be my galvanic cell using this reaction. So I want to talk about shorthand notation for galvanic cells next. Well, this, after you've gotten used to it and drawn a few, doesn't take very long. It's kind of annoying to draw that every time you want to represent a galvanic cell. So we do have some shorthand notation, and I'm going to leave a little bit of space because I'm going to go back up and draw the shorthand notation for that one. So just leave yourself a line or two. So shorthand notation for galvanic cells. And this is going to sound kind of confusing at first, probably as most things, but just kind of bear with me. And then when we apply it to an example, hopefully it'll make a little bit more sense. But we're going to have a single vertical line to represent a phase boundary. So remember, if we said something is in different phases, different states of matter. So if I have a solid and an aqueous solution between them, I'm going to draw a single vertical line. So a single vertical line, we should have just squeezed that in here so you know what I'm talking about. Literally, it's a single vertical line. So just like that. Kind of looks like an L, but it's just a line. A double vertical line so 2 lines, is going to represent our salt bridge. Basically, it's going to represent the boundary between the 2 half cells. The anode half cell is written on the left side of the salt bridge symbol. When you were drawing our cell up here, I said that it's standard to put the anode on this side, but you could switch them. Here you cannot. It's actually incorrect if you write it the other way. So my anode does need to be on the left-hand side. And that's kind of why we tend to do it this way, just so it's consistent and not as confusing. But the anode, again, maybe we should use a different color, needs to be on the left. And then that means that the cathode is going to be on the right. So the cathode half cell is written on the right side of the salt bridge symbol, the double vertical line. So cathode goes on the right. And then the reactants of each half cell are written first, followed by the products. If they're in the same phase, right, they have the same state of matter. And the reason we're kind of using phase instead of states of matter is that aqueous solution isn't really a state of matter, but it is a phase. So if they're in the same phase, we're just going to put a comma between them instead of a vertical line, because that vertical line is representing a phase boundary. So I'm just going to kind of add this here. If the reactants and products are in the same phase, and we will do an example like this, use a comma between them. So let's go up and write our shorthand notation here for this one we just did. So I'm going to have my anode first. We're going to start with that, all right, because my anode goes on the left of my salt bridge symbol. I'm going to write the reactant first, followed by the product. So if I go back up, my reactant is zinc solid. My product is zinc 2+, which is an aqueous solution. I didn't put that there, but those are different phases. So I'm going to have my zinc solid. Because zinc 2+ in aqueous solution goes next, and those are in different phases, I'm going to draw this single vertical line. I'm now going to have my salt bridge symbol. I'm going to write my cathode compartment, my reactant first, which is lead 2+. It is an aqueous solution. Phase boundary, because my product is a solid. So this would be the shorthand notation for this galvanic cell. Let's go back up and do this one. So do this one on your own real quick, if you wouldn't mind. So hit pause, write your shorthand notation for this one, and then when you're ready to check it, hit play again. All right, hopefully you guys did that, and we're gonna squeeze it over here on the side. So anode first. So my reactant is a solid, my product is an aqueous solution. So we need to have that vertical line between them. And I, of course, did not give myself enough room. I now have my salt bridge symbol, basically the separation between my anode and my cathode. Copper 2+, which is aqueous, and then copper solid, which is solid. Sorry, that was redundant, but this would be my shorthand notation for this one. Cool. So going back down, just kind of what happens, and we'll do an example, but if you don't have a metal, right? If I look at this one, going back up again, sorry, keep scrolling, right? Both of these, I had something that was solid. Right, I had solid here, I had solid here. So those pieces of solid, or those solids, sorry, are my electrodes. You physically need a solid piece of metal to hook that wire to. So if you're looking at a reaction where everything is ions, now you have a problem because you don't have something solid to attach that wire to. So if there isn't a solid that is being oxidized or reduced, we should say and or, because you actually need both, right? We need one that's being oxidized and we need one that's being reduced. An inert solid, and it's going to be metal, let's say that an inert metal is used as the electrode. And the most common example for this is going to be a piece of platinum, so usually platinum. So if you are using platinum, that does need to be in your shorthand notation. So let's go through an example. We're going to design a galvanic cell and write the shorthand notation for the following reaction. And I want to use iron solid plus 2 iron 3 plus going to 3 iron 2 plus. So this one might look a little confusing, but we're going to do it together here. So we do have to split this into 2 half reactions, right? We need to have a half reaction for my anode compartment, right? My oxidation. We need to have a half reaction for my reduction compartment, which is my cathode. So I only have one product, so we're going to have this like go to both of them. If that makes kind of any sense at all. So I'm going to have iron solid going to iron 2 plus. Right? And this is going to be my oxidation, right? My oxidation number here is 0. Here my oxidation number is +2, so it lost electrons. And then balancing this using the method that we have learned previously, right? I need to get my electron counts the same, so I'm going to add 2 electrons to this side, right? We already said it's our oxidation. My electrons are going to be produced, right? We're losing them, so this makes sense. My second half reaction then, I'm going to use my iron 3 plus, and then it's going to iron 2 plus, right? I only have one product, so it has to be going to the same thing. If we look at our oxidation numbers, right, this is a +3, this is a +2, so it is a reduction, right? I'm gaining 1 electron. So we'll write that over on our reactant side. And then to balance this, right, remember balancing them, we need to have the electron counts equal for both half reactions. Because I have 2 here and only 1 here, this second reaction, right, my reduction half reaction needs to be multiplied by 2. So this would actually be 2 electrons, 2 iron 3 plus, right, which is what we have here, and then going to 2 iron 2 plus. And then when we add those together, right, we would have 3 of these, which is what I'm seeing in my equation. So my 2 half reactions, right, this is my oxidation, and this is my reduction. And when we write our shorthand notation, we don't necessarily need to show that there's 2 of these. We can just show that it's iron 3 plus. And then the same here, we don't necessarily have to have the 2. Sometimes it's included. Sometimes you'll actually see concentrations included, like you would have iron 2 plus, and then sometimes in parentheses, they'll do like 1 molar, that sort of thing. So if you see concentrations in there, that is somewhat common, not necessarily required, but you will see that sometimes. So let's draw our cell here. So my 2 half cells, my oxidation is going to be my anode. In my oxidation, I have iron solid going to iron 2 plus, plus my 2 electrons. My cathode is going to be over here. That's going to be my reduction. I have my 2 electrons plus 2 Fe3 plus going to 2 Fe2 plus. And then drawing in my metal, on my anode it's not a problem, right? Because I have iron that is solid, so Fe solid. If I look at my cathode compartment though, these are both aqueous solutions. I guess I didn't actually write that, but if they're ions, they're in solution. You're not going to have a solid ion or a liquid ion. So if you have an ion, it is in solution. So those are in aqueous solution. So I don't have a solid on that side. We do need to have a solid, however, to actually hook our wires to. So what we're going to use is we're going to use a piece of platinum. And then I'm going to connect those with my wire. My anode is my negative side. This is my positive side. My electrons are still moving, right, from my anode to my cathode, right? I'm producing them on the anode side. I'm consuming them on the cathode side. in solution here, I have iron 2 plus. Here in solution, I have iron 3 plus and iron 2 plus, right? Both of those are in aqueous solution, so they're floating around. My salt bridge, I didn't specifically say, so I'm just going to use sodium sulfate again. Anions towards the anode, cations towards the cathode. So that would be my cell for this one. My shorthand notation, again, we're going to write our anode first. We're going to do our reactants first and then our products. Those are in different phases, so I'm going to put a vertical line between them. My salt bridge symbol, and then on this side, same thing. I am going to put reactants first and then products second, but they're in the same phase. They're actually both aqueous ions. So I'm actually just going to put a comma between them. And then I do have to include that platinum. So now I'm going to put my phase boundary and then a PT for my platinum electrode. Again, these were both aqueous. Because they're the same phase, right? I'm not putting a vertical line between them. So this is how I would write the shorthand notation for this one.